Okay, good day, Professor and everyone. We are from OpTeamPrime. My name is Imam, and my teammates are Kangsan and Rustam as our team leader. Today, we will present our project entitled LSTM versus Transformer Encoder for text classification. This presentation consists of four parts: introduction, experimental, result and discussion, and conclusion. So, let's begin with the introduction. The text classification is one of the fundamental tasks in natural language processing. Its goal is to automatically assign categories to text documents, such as a news article. In this study, we compare two popular deep learning architecture, which is LSTM and Transformer Encoder. This model represents different approaches to a language understanding. LSTM learns through sequential memory, while the Transformer Encoder uses self-attention to model relationship between the words. Our objective is to evaluate how these two approaches perform under the same training condition. To evaluate both model, we use the IAG news dataset, which is a widely used benchmark for text classification. The dataset contains four categories, which is world, sport, business, and science and technology. The data is divided into training, validation, and testing set. In addition, the class distribution is balanced across all categories. This helps ensure a fair comparison between the two models. Before training, the text must be converted into numerical representation that neural network can understand. We apply the same pre-processing pipeline to both models, including tokenization, vocabulary construction, and sequence standardization. By keeping the pre-processing identical, we ensure that any performance difference comes from the model architecture itself. Now let's look at the two models being compared. The first model is LSTM. Unlike a standard LSTM, we use a bidirectional LSTM. Take both forward and backward directions. This allows the model to capture richer contextual information. Second model is Transformer Encoder. Instead of processing words sequentially, it uses self-attention to analyze the relationship among all words simultaneously. In simple terms, the LSTM learns through memory, while the Transformer learns through attention. This slide visualizes the architecture of both models, but begin with a word embedding and end with a classification layer. However, the process information different. The LSTM relies on a recurrent memory, whereas the transformer relies on self-attention to capture relationship across the entire sequence. Well, to ensure a comparison, both models use the same embedding dimension and training settings. However, the internal architecture are different. The LSTM contains approximately 4.9 million trainable parameters, while Transformer contains about 2.8 million. Therefore, LSTM has a larger model capacity, while Transformer is more compact and efficient. In the next session, we will see how these differences affect the performance.
Now I will explain our experimental setup. This part shows how we trained and evaluated the two models under controlled conditions. To ensure a fair comparisons, both models used the same dataset, split, vocabulary, tokenizer, optimizer, learning rate, batch size, and maximum sequence length. We used all stopping, gradient clipping, and 3 random seeds. The models were evaluated using accuracy, micro-response score, loss curves, confusion metrics, calibration, inference speed, and attention visualizations. This slide shows how each model was implemented. The LSTM uses embedding bidirectional LSTM layers, dropout, and a linear classifier. The transformer uses embedding, positional encoding, and self-attention layers, mean pooling, and a linear classifier. We conducted a dataset size evaluation study using 25%, 50%, and 100% of the training data. The goal was to compare data efficiency between LSTM and Transformer. We also analyzed hyperparameter sensitivity, learning curves, and failure cases. This table summarizes our experiments. The main comparison used all stopping and 3 seeds, while the evaluation study used different training data size. We also included hyperparameter sweep, learning curves, and failure analysis. Now I will move on to the results and discussion. Overall, the LSTM slightly outperformed the Transformer Encoder. The LSTM achieved 92.6% test accuracy, while the Transformer achieved 92.37%. The micro-reference score also showed a similar result. However, the difference is small, so both models performed competitively. The transformer converged faster, usually around epochs the 1 or 2, but showed early overfitting. The LSTM converged more slowly, but achieved better final performance. This slide shows the gradient stability during training. Both models had similar initial and final gradient norms. Gradient clipping was mainly active only at the beginning. There were no vanishing or exploding gradient problems. Overall, both models were stable, but
Here we analyzed confusion matrices and per-class performance. The key findings is that Sport was the easiest class with 97% precision and 98% recall for both models, and with F1 score 0.97. So also we found that the business side tech was the hardest class, and you can see from the errors as it has almost sharing the same distribution with those models share the same distribution, the errors. So it means that both models struggle most with business and sci-tech distinction. This is the main sort of miscalculation in dataset rather than the architecture. Here we've done the ablation study of data set size. So the first thing is that in the graph you can see that transformer at the beginning with 25% of data set show the highest results. And while we increased the data size, the LSTM started to overtake the transformer at both test accuracy and test macro F1. This gives us a key insight that transformer strong with limited data because of the attention mechanism. So while the LSTM is benefit more data flow with more data, and here we analyze bias and variance. So the first takeaway here is that train and validation gap decreases as the data set increases for both models, as you can see here. So also transformer shows us that uh, it will have a higher generalization gap compared to LSTM, as you can see at the end, with full data set. And also both models are not high bias at full data set. We can see here that they all have the old transformer and LSM had the validation accuracy of 0.92 to 93. From hyperparameter sensitivity, we can find that transformer is very sensitive for learning rate tuning, while the LSTM maintain relatively stable performance over the all learning rate range. While the dropout rate very interesting, here also LSTM we can tune and find the optimal condition, but for transformer it is very negligible. When we tried embedding dimension tuning, we found that LSTM very prefer increasing dimension, while the transformer lost its accuracy. Here, I will not stop too much in calibration and inference cost. In one sentence, I would say that both models are reliable in terms of confidence calibration, but Transformer offer a major efficiency with 2.8 times faster inference, which makes very superior choice for real-time and high-volume deployments. In order to develop our experiment, we've done further analysis like failure analysis, and in this we had misclassified examples from the best seed, like 42 checkpoints and with 7,600 sample tests. So first we've done error overlap and taxonomy. For more details, you can refer for this slide. And next we've done representative misclassified examples. This is also very interesting findings. For the transformer, we also visualized that attention map, and we found very interesting findings. Please refer for this slide. In conclusion, from our project, the important takeaways is that the LSTM achieves slightly higher performance with some limitations in convergence speed. The Transformer Encoder is very data efficient at small data size, while the LSTM can better work with more data. Both models struggled with the business and Sci-Tech classes. The Transformer can be sensitive to learning rate tuning, while the LSTM is better calibrated. At the end, I would say that both models deliver reliable, confident calibration, while the Transformer achieves 2.8 times faster inference, which makes it superior choice for real-time and high-volume deployments. Thank you for your attention.